you very much for the kind words and the invitation to talk about this slightly different topic than probably you're used to hearing about here. So I'll tell you about simulating collider physics and on quantum computers using effective field theories. And the paper is with Christian Bauer and Ron Freitas, and the archive link is at the top. So let me dive right into it. I start most of my quantum computing talks with a quote from Feynman, which I think is suitable given that he's one of the ones credited with originating the idea. He says, I therefore believe it's true with a suitable class of quantum machines, you could imitate any quantum system, including the physical world. So I'll first tell you a little bit about what quantum machines are in the sense of quantum computers, before I talk about our EFT strategy and how it's related to energy physics. And then I'll discuss the particular calculation that we've made, in particular, certain soft function in massless scalar theory. And then I'll talk about some of the challenges that we have with current quantum computers. And then finally, I'll say a little bit about the future, but I'll be pretty brief about that. I'm not going to talk about other work that we've done in the context of parton showers, which is related to EFT, but not exactly the same. And so, but I'm happy to talk about that also if you have questions. Okay, so first let me talk about quantum computers. So the goal is to implement our systems Hamiltonian, for example, the one we care about a lot here is the standard model, in a proxy system, which would be our quantum computer, and then let it evolve. And first question is what can be the proxy system? So it can be anything really. So it could be like a collection of spins in some tabletop object. It's very cold, relatively small, and the best quantum computer is one that looks most like the thing you're trying to simulate. So if you're trying to simulate, an array of spins, the best quantum computer is just an array of spins. Then you could mimic exactly the thing you want to emulate. You make some measurements and you can make some predictions for the thing you're trying to learn something about. Now, the challenge for us is that the thing we want to emulate, for instance, is like high energy particle scattering. So this is, for instance, an aerial view of the Large Hadron Collider. We'd like to make predictions for high energy scattering, and the best quantum computer for the LHC, for instance, would be another LHC. So if you have many tens of billions of dollars to spare, you could perhaps build a very precise quantum computer for the LHC, but it wouldn't be incredibly useful, in part because we could make very accurate predictions, but we wouldn't be able to learn the underlying dynamics. And so the real goal, of course, is to take a quantum system using, say, a set of spins where we can encode the physics that we know about and then emulate some particular aspect of high energy scattering. And the number of possibilities is really endless here. And the key is really efficiency, because we want to do this with limited quantum resources, given the current limitations in terms of the number of sort of individual degrees of freedom that we can have, and also the amount of time that they can remain coherent for. Okay, so let me say a little bit more about quantum computing before I get to the high energy physics. There's no consensus on like what a quantum computer is. For all of you that are watching this through your desktop, there's basically a consensus on classical computers, how to construct them. And there's a variety of different possibilities, for instance, using various kinds of superconductors and other possibilities. Now, this is not going to be a hardware talk, although it's a very exciting topic, but I'd like to flash this picture just to kind of give you a sense of where we are. So the left picture here shows an IBM computer from the late 60s, and it's roughly the size of a room, takes multiple people to operate, and has relatively little computing power. Whereas on the right-hand side, this is one of IBM's quantum computers, roughly from now. It's in that dilution fridge you can see in the middle of the room. And it's, once again, roughly the size of a room, requires multiple people to operate, and has relatively little computing power. So it really feels in a lot of ways like where in this exciting time where the quantum computing is sort of being defined and refined and very rapidly. So I can say, having only been in this field for a small number of years, that even running sort of similar algorithms on quantum computers over the last few years, that the fidelity out of the box is just improved dramatically, which is really exciting. Okay, So the core component of a quantum computer is a qubit. At least there are other systems that are possible. We often use these binary systems, so qubits, which is an abstract representation of a quantum system that can mean a superposition of two states. So you can think of it like a spin. Underlying what's going on, there are a variety of different ways you can implement a qubit, which I'm not going to talk about. Now, the best quantum computers that exist, they have order 10-ish qubits. Each qubit has roughly one connection, order one connection, so maybe a couple of connections to other qubits, and can stay coherent for, say, like thousands of operations before you lose coherence. And just to give you a sense of what these things look like, so this bottom left picture is a schematic diagram of one of IBM's quantum computers. So this one has 20 qubits labeled 0 through 19. And you can get a sense for the connectivity. So it's not like if I have 20 qubits, every qubit's connected to every other qubit. You can see that most of the qubits have only 2, 3, and in some cases 4 connections to neighboring qubits. So it's very far from being a fully dense connectivity graph. Okay, and just like a classical computer, the point is that you can program a universal quantum computer. And I'm going to show you some programs for our effective field theory algorithm later. So I want to give you a little bit of introduction on what a quantum program looks like and how to read it. So here's a quantum program. It's relatively simple. It has 3 qubits, and they're written as these cats on the left-hand side with a 0. That means initialized to the ground state. So it's sort of like the start of a program. It usually looks like that. And then there are a series of operations that are applied to the qubits. And the operations that you have to apply, that you can apply on a quantum computer, have to be unitary. So the U is just to remind you that it's unitary. And there are different kinds of operations you can apply. So for instance, this bottom one, this U1, is called a single qubit gate. So it's a unitary applied to a single qubit. So you can think of this as basically a 2x2 matrix that's acting on this single qubit, which is a superposition of 0 and 1. And it's only applied to this qubit. So this basically mixes the state 0 into a superposition of 0 and 1 with some rotation. And then you can do conditional operations. So this qubit says apply U2, the U2 unitary operation to this qubit, the second one, if the first qubit is in the 0 state, otherwise don't do anything. And the same as here. So there's a 1 applied if in the 1, otherwise do nothing. And because this is in the superposition of 0 and 1, both this and these two operations, they both get applied, but only to a part of the state, this third state. You can do more than having single qubit operations. So for instance, this block here says conditionally on this first qubit, you apply some bigger unitary operations. This is now applying to 2 qubits at the same time. So if you like, you can think of it as sort of a 4x4 matrix. That's conditional on what's going on in this first qubit. And then at the end, this symbol here, which is supposed to look like a meter of some kind, tells you to measure. So you measure all the qubits, and then you collapse the wave function, read out the state. And for a lot of the things you want to do, you have to perform, you do this whole operation many times. So you initialize to 0, you perform these operations, you make a measurement, and then you collect some statistics of the various measurements to try to learn something about expectation values or whatever else it is that you're trying to do. Okay, so that's roughly speaking how a quantum program works. Now there are some challenges I want to quickly highlight. So in practice, you have to decompose all of your operations. So I showed on this slide this multi-qubit controlled gate. And in general, that's not allowed because you have to decompose. So given a quantum computer might have only a small number of operations that are possible. And typically you can do single qubit gates like these ones. And then there's typically only a small number of multi-qubit operations. And the most common one that people have is this thing called a CNOT, which is shown here. So it swaps the state if 1, swaps the state here if this is 1, otherwise it does nothing. And there's a theorem that says that you can decompose any multi-qubit operation into single qubit gates, so like the CB&A and these CNOTs. And so you can see that's done for, this is a particular identity that one can prove, where you have some unitary operation U and you can decompose it this way. Now there aren't really compilers So a lot of cases you have to do this by hand. Now there's this is a really hot topic. So this is a rapidly evolving situation. There are some compilers, but it's far from the standards that we have for say C++ or other languages on classical computers. The other thing which makes it complicated is that the circuit implementation is architecture dependent. So imagine if you're going to go into a different computer or run a job on a different computer. I mean, sometimes you do have to do something different for the environment, but you don't really have to usually worry about the underlying hardware architecture. But for instance, if you have a machine that looks like the one on the left versus the one that looks like the one on the right, there are different connectivity patterns, and you might want to put your qubits of your algorithm in different places. And it's particularly complicated because you can't copy in quantum computers. There's no cloning, no clone theorem, right? So you can't copy information. All you can do is move, so you can teleport. And the last thing I'll say before I get to the high energy physics is that current quantum computers are pretty noisy. So here's a plot I like to show where it doesn't matter what the observables are. I removed them from the graph to make it simpler. You can see the original reference for information, but basically there's some physical quantity versus some other physical quantity, and the nominal output of the quantum circuit is in this teal color. And then to get the other colors, every C naught is replaced with an odd number of C naughts. And the thing about the C naught is that the C naught squared is the identity. So if you replace every C naught with 3 C naughts, for instance, it should do nothing to the output. However, you now have triple the number of gates, at least the number of 2-qubit gates in your circuit. And same for 5 and 7. And so what happens is basically by adding more gates, you're just injecting noise because you're not changing the nominal value, but you're adding more noise. And you can see that the value of the observable, whatever it is changing. And so there's the nominal value, and then you add more noise, and basically it goes up, and it sort of becomes this flat line at 0.5. And so this is actually a strategy that's used to mitigate errors, which I'll say more about later. But for now, you can see that this is a pretty big problem. Okay. So this is sort of my last slide of introduction before I get to the EFT. So I think caveats aside, these challenges, there's a good reason to be excited. There have been impressive leaps in hardware, as I mentioned, also in firmware and software. So the algorithm side, which is the area where I work, in recent times, and I think interest has clearly exploded, although some of it may be misguided. Now the question is, will you have a quantum processing unit on your laptop 5 years from now? No, probably not, and certainly not in your iPhone. But you may be able to run on a quantum processor in 5 years that allows you to make a calculation that was not possible before, which I think is quite exciting. And certainly in the slightly farther future, where we might have fault-tolerant quantum computers, which I can say more about later, then there might be a possibilities of making a variety of calculations that we couldn't make before. Okay, so now let me get to QFT. Right, so one of the early adapters of quantum computing has been quantum chemistry. And one natural question is, why is quantum field theory more challenging than quantum chemistry? And the answer is because we have continuous degrees of freedom. So every space-time point has a quantum number, and they're discrete and continuous quantum numbers, which makes things challenging. Now, there was some pioneering work from almost a decade ago now that showed that it's possible to, in principle, to simulate the time evolution of a quantum field theory in polynomial time. So that is to say that you can, in principle, simulate scattering, for instance, using efficiently on a quantum computer. Now that paper doesn't actually implement the circuits, in part because the number of gates required is pretty enormous. So let me walk through a little bit some of the numerology that motivates what will come next. Okay, so the ideas of doing scattering on a quantum computer have largely focused on ab initio calculations using lattice methods. So as I mentioned at the beginning, I'm not going to talk about alternative approaches like parton showers and other calculations that we could speed up. I'm also not going to talk about other aspects of quantum computing for high energy physics. I'm really going to focus on the EFT connection, because that's the context for this workshop, this seminar series. So just to be clear what I mean by lattice methods, so we discretize space and time and then digitize the field values to make the infinite dimensional Hilbert space into a finite dimensional one. So just to put in some numbers, let's say we digitize our fields into some number of values, so n sub 5 values. And this is going to be suggestive because I'm going to later introduce phi as the field in the EFT we're going to write down. And then let's say we have n lattice space points in each of the d directions. So then our Hilbert space has this size. So it's a pretty huge space. I'll put some numbers to this in a second. Now in a quantum computer, the nice thing is that you only need the log of that number of qubits because qubits can store a lot of information. So if, let's say, in a given dimension you have n lattice, or you have n phi field values, then you only need log n phi qubits to represent that. So that's great. That takes us down to this number, although n to the d is still a huge number, which we'll see in a second. And just to give you kind of a sense, these plots will show up again later, but let's say I have a field value. This is like, say, a Gaussian distribution, the blue one, and it's digitized into 8 points. And so you would need, for instance, so log base 2 of 8, so you need 3 qubits to represent these 8 points. And let's say this is just the ground state of, this is a ground state of a simple harmonic oscillator, for instance, and this is like the first excited state. Okay, I'll come back to this later, but this is just to illustrate what it looks like if you have 8 field values per dimension, and if you have, say, 3 dimensions, that's what it would look like. You know, if you had n equals 3, d equals 1, and then n phi equals 8. Okay. So putting in some numbers, discretizing and discretization and finite volume effects introduce cutoffs. So if the smallest lattice spacing is delta, then the approximation of the continuum theory is good only when the energy is above this value and below that value. Oh, actually, I think I have it backwards. Sorry, should be the other way around. Anyway, the point is that if we want to cover dynamics, from sort of the smallest energy scales of 10 to 100 MeV all the way up to the beam energy of the LHC, that means we're talking about capital N here, sort of like a million or so. And so that corresponds roughly to like 10 to the 18 qubits that would be required. And I suspect that will be more than we'll have in our lifetime, probably. But there's a solution to that problem, which I think you all know, and that's sort of the motivation for this talk, which is effective field theory. So the idea is that we know how to decompose, for instance, like hadronic physics at the LHC into multiple components, and some of those components they're very well known using perturbation theory. And so the idea is, let's use the tools that we have, so perturbation theory, to cover the highest energies where perturbation theory is most valid, and then and also in those cases, that's where you need the finest lattice spacing. So we don't have to worry about that. And then in the cases where where perturbation theory breaks down, we can try to calculate the objects in the theory using, for instance, quantum computers. So here's, for instance, soft collinear effective theory. There's the hard function, jet functions, n of them, and the soft function. And the hard function is what encodes the matrix element with all the highest energy dynamics. And then these other objects are have lower dynamic range. And the key is that if we don't need the full dynamic range of the LHC, we can get away with far fewer qubits. And so if you put in some numbers, you can maybe get away with millions or billions of qubits. And while that's still a huge number and very far from the number of qubits I said we have now, so I said we have tens of qubits now, I think that it's not crazy that we could have millions or billions of qubits in the not too distant future. Although I won't give you a date in the future by when we'll have this. Okay, so now I want to start working towards how we could actually implement some prototype on an existing quantum computer. And let me walk you through how that's going to work. So I want to focus on the soft function. In this case, basically the high energy physics the high energy particles do not contribute to the dynamics. They're basically static Wilson lines where there's some charged particle that's going at this the speed of light along some light direction, and then we can compute these objects here, where n is the direction, a is in this case the soft gauge field, this is the kind of thing that we want to sort of work towards. Okay. So the matrix elements that we care about, say for instance you have two high energy particles back to back that are going away from each other, the kind of object we want to compute are these matrix elements here. So you have the vacuum, and then you have this time-ordered product of these Wilson line objects, and then you can compute the overlap with some other state. So X could also be the ground state. That would be like there's no emissions, and then but X could be any other excited state as well. So this is the matrix element object that we're going to try to work towards for the remainder of the talk. Okay, so our goal, of course, is to get to the standard model, and in particular QCD. But we want to take concrete steps to achieve certain milestones in order to get there. So given current resources, let's take a simpler problem. And so we're going to do 1 + 1 massless scalar theory instead of gauge theory. Now, clearly some of the complexity of the full theory is lost when we do this, but it has many of the salient features. And so the interpretation here of the object as a soft function in SCAT is sort of lost, but the objects that we're going to compute will look a bit like the ones we want to compute in the full theory. And so I think we'll learn some valuable insight. We'll develop some valuable insight by doing this prototype calculation. So here you can get a sense for the kind of things we're going to calculate. So the Hamiltonian looks like this. So we have our field phi, and so this is basically pi squared plus phi squared, and then we have our Wilson line. I didn't write the one for y bar, but it looks very similar, just going the other direction. And there are a couple of subtleties about 1 + 1 dimensions that are don't generalize to other dimensions. So for instance, in 1 + 1 dimension, there are no transverse directions, obviously. And so even all the soft modes are also collinear. So there's no collinear safe observables. So the thing we're going to calculate, the soft function itself, is not a collinear safe observable, but that's okay. It still, I think, gets us close to calculations that we care about. And when we go to beyond 1 + 1 dimensions, this is a problem that we'll be able to solve. Although the quantum resources required to do that are currently prohibitive, but I think we're close to being able to do that. Okay. So the first thing we have to do is we take our continuum theory and we want to discretize it in space. And so here's our discretized Hamiltonian. It looks basically the same. The difference is that we now have these phi I. So phi I is the field evaluated at a discretized point in space. And we have a one-dimensional lattice. This is a one-dimensional theory. So it just is a sum in one dimension across our capital N lattice points. And there's a spacing between lattice points delta x. And the objects we're going to compute are these Wilson line-like objects, which look very similar to the ones I wrote down earlier, except now you see we're moving along just the one dimension that exists. And there's the phi evaluated at various times along a light-like direction. And this n0 here is the center of the lattice. So we have, you see there's the center of the lattice, and then we're moving, there's these yn and yn bar sort of representing opposite directions, either to the right or to the left. And then, yeah, operations like this delta here are finite differences between different between different lattice space point, neighboring lattice points. And in particular, these are local operations. Okay. So then, in addition to discretizing space, we have to digitize the fields, because we still have to put this on a digital quantum computer, which has binary representations. And so we have to decide how to discretize the field phi. So at every lattice point, there's a finite number of values of the field. And this is a plot I flashed you earlier, but now let me spend a little bit more time explaining it. So in this case, this particular example I'm showing down here, there are 8 values, which means that there are 3 qubits that are used to represent it. And you have to decide how to space, like where to put the points. And so let's say you want to have uniformly spaced field values, then what you have to figure out, given some number of qubits, is like what the endpoints will be. So you have some maximum phi value. And it's kind of actually pretty simple to see what the optimal spacing, what the optimal values should be. Basically, if you think of the Hamiltonian this way, so it's sort of like a conjugate momentum operator, and then like a conjugate field operator, and then the field operator squared. This really suggests that if you in this definition or redefinition of the fields, then it's pretty clear that because they have the same form, you really want to have the same precision for both the field and the conjugate field. And so if you write down, let's say you put down some lattice points for the field as shown here, you can figure out what the maximum momentum or conjugate field values are. And by setting the ranges to be equal, that just tells you right away what the maximum value is. So these are like the digitized position. They're 0 through 7, but they actually correspond to some particular values of the field. And once again, now this case, for instance, here is the Gaussian, and then the blue is the ground state, and then these are the excited states. And anyway, that's the setup. Okay, so now let me work towards the actual quantum circuit we want to construct. So as I mentioned, these are the objects we want to, these matrix elements are the ones we want to actually build. And there are, roughly speaking, 3 components. Well, so the first thing we have to do is these are the input qubits. And so these look a little bit, these look the same as what I showed you earlier in the example quantum code I wrote down. The difference is there's this little slashy thing here. And so the slashy thing basically means that this is not a single qubit, but this is supposed to represent a register of qubits. So there's L0 up through Ln-1. And basically these qubit registers each represent a lattice site. And at each lattice site, we digitize the field. So there are n phi qubits in each of these registers, so that we can encode 2 to the n or log n phi qubits, so that we can encode n phi values of the field. Sorry, it should be log n phi qubits per lattice site, and there are capital N lattice sites. Then the first thing we want to do is we have to prepare the ground state, which is the vacuum. And I'll describe in a little bit basically each of these steps. So we build the vacuum, and then we evaluate this time-ordered product that's shown here. These are all unitary operations that have to be applied to the state. And then to make the measurement, we then evaluate the inverse state preparation. So if x here is omega, then it's basically just the inverse ground state preparation. That would tell us the overlap with the vacuum and sort of the no emission probability. And then, but x could be the excited state, so it would be the inverse of the excited state operation. This is unitary, so it has just the conjugate transpose is the inverse. And then at the end we make a measurement. So these are the measurement symbols. Okay, so now I'm going to walk through each of these pieces sort of one at a time. So let's first start with the state preparation. So in general, preparing a generic state requires exponential resources. And there are efficient exponential algorithms. So I say efficient in quotations because exponential means it's not efficient, but the sort of the best you can do is something like very close to, if you have k qubits, 2 to the k, you can get very close to 2 to the k, basically. So that's not good, because if it requires exponential resources to prepare the state, then that would sort of defeat the purpose of a quantum computer. The whole point is that we only want to do things that require polynomial resources in general, because then we might get a quantum advantage. Okay, so that's unfortunate. However, for any particular state, there might be shortcuts. And in fact, for us, there's good news, which is that we care a lot about Gaussian states, multidimensional Gaussian states, because those are the ground states of our theory. And there are algorithms that require only polynomial resources for multidimensional Gaussians. And in particular, the paper that everyone cites is this interesting paper from Kataev and Webb from a while ago that describes an algorithm that he would do this. So the algorithm is basically 2 parts. So one is that you first build uncorrelated Gaussians. So if you have n lattice sites, you have n Gaussians. And then as a second step, it applies some shearing operations to introduce correlations. And these two operations are each polynomial, so the whole thing together is polynomial. Now, we've done some investigations in the context of thinking towards quantum field theory, and we find that these two parts don't have equal scaling. In particular, the scaling of the first part. So this paper, Digitizing Web, it lays out the algorithm, but once, just like the science paper that laid out the algorithm for quantum field theory in general, for scattering, that this doesn't actually implement the result because it also requires a lot of resources. So we find that the scaling of the first part, the multidimensional Gaussian part, that has a very large, it's polynomial, but it has a very large prefactor. And so we find that, if we only need a small number of qubits per lattice site, which I'm going to show in a little bit is most of the time, it's all we need, especially if we don't care about very high frequency modes. I mean, typically we're going to have a small number of particles and excitations that don't require having high, being in a high excited state everywhere in the lattice. And so we need a small number of points per lattice. We want to have many, many lattice sites. And so for that, it actually might be better to use an exponential algorithm, so generic exponential algorithm for the independent Gaussian state prep, and then use the Digitizing Web like approach for shearing. And stay tuned for a more detailed explanation of all that shortly. So we're just finishing up some details where we'll describe in great detail this algorithm, or the Digitizing Web algorithm, its various components and implementation, and then how it can be done efficiently or done effectively, let's say, using current resources. All right, so that's the state preparation. Here, just some plots to give you a sense. So let's say you have 3 lattice sites, and here, once again, you can see there are 8 points, and phi is 8, and there are 3 qubits per lattice site. This is sort of projecting, so you can see the Gaussian states for each of the 3 sites. And there are sort of 3 things shown here. There's an analytic calculation of what it should be, the discretized field, discretized theory, ground state. And then there's this Digitizing Web approximation, which is not exactly the same as the analytic. It's an approximation that gets better the more qubits you have. And then there's an implementation, this thing called Qiskit, of the approximation like Digitizing Web. And you see that it matches basically exactly because it's doing the same thing. And so Qiskit here is one of the common software packages for implementing quantum algorithms. And that's the one that we're going to use for the rest of this talk. And here you can see the multidimensional version of that, at least projecting the pairwise correlations between various sites on this lattice. Okay, so then the next step of the whole algorithm is the time-ordered product, and this piece requires multiple components, which I'm just going to kind of wave my hands a little bit, but I'll try to give you at least a sense of the various pieces. So the first important piece is that we can write the field operator as a sum over sigma z matrices that are independent per lattice site. And so in particular, our per lattice site. Per qubit. So we have a given lattice site, for instance, you have, say, n phi qubits, and you can apply these alpha I coefficients are known. I just didn't write it down to not obscure the formula. And then these are poly sigma z matrices, which are applied to a given qubit. And so this is relatively simple, and means these are sort of single qubit gate operations. And then everything else is sort of built from this phi. And because it's relatively simple, then this is possible to build more complex objects from. And so the kinds of things we want to calculate are, we basically want to calculate e to the IHT, right? That's the time evolution. And H is going to have 2 components. There's the one component, which is like the conjugate momentum part, or the conjugate field part, and there's the field part. And so the way that this is done is using the very common formula for trying to take the exponential of non-commuting operations. So these, obviously the pi and the phi operators don't commute. So one way of breaking it apart is the Suzuki-Trotter formula, which basically you take this e to the IHT and you break it up into these 2 parts. And so this lowercase n here is just the order of the approximation. So it's a free number, and usually people use 1 or 2. And you can see there's this first part is the pi part, and this is the phi part. And so the phi part is pretty clear. It's just it's an exponential of sort of phi squared, and there are ways of implementing that. And then the complicated part is this conjugate field part, and that's done using some quantum Fourier transforms. And so basically this e to the I h pi t, which is the pi squared part of the Hamiltonian, you can get that from operations on the EDI phi squared component. And so roughly speaking, these are the different ingredients that are required to sort of put things together and then build up a quantum circuit that implements the full time evolution. And then that's the setup. And now I want to describe in the remaining minutes that I have an actual measurement that we did on current quantum computers. So we used an IBM computer. It's called IBMQ Manhattan. It has 65 qubits, but we didn't use all of them. We just used a small subset of them. We used 3 lattice sites with n phi equals 4. So that means 2 qubits for lattice sites, and therefore 6 qubits total. It turns out that with only 3 lattice sites, the Wilson line operator simplifies significantly. So you have there's the middle point and then 2 endpoints. And so basically the time order products are such that the evolution operators act on initial or final eigenstate, the Hamiltonian. And so basically everything cancels except the middle term. And you're left with basically just this operation that's shown here. So you have this EDIG delta x, which is the lattice spacing, and then this difference in field values, the one on the right and the one on the left. Yeah, maybe just to quickly say that actually just to give a sense of the resource scaling. So this top left plot shows the number of multi-qubit gates that are required as a function of the number of qubits per lattice site for 3 lattice sites. And the Wilson line operator actually doesn't require any multi-qubit gates. It just requires single qubit gates. But then there's the state preparation and the Hamiltonian evolution. This TS equals 1 is the Suzuki-Trotter formula with that little n I mentioned earlier equals 1. And you can see this really rapid scaling of the number of qubits required. And in fact, if you have 2 qubits per lattice site, which is what we have, if we didn't cancel this term, then we would require something like 70 CNOT gates. So that's this plot shown here. And then this bottom right plot is the number of single qubit gates. And the reason I'm less worried about single qubit gates is because they're less noisy. So the multi-qubit gates, which makes sense, entangling gates, they're noisier, they're more involved, whereas the single qubit gates, it still requires a lot of them. So you can get a sense for the number that are required here, but it's far less. And in particular, if we use 2 qubits per lattice site, the Wilson line and state preparation, they require something like 10-ish qubits total. Okay. So here is actually just the circuit. I thought I would print it for you just so you can have a look at what it looks like. It's a little bit different format than what I showed earlier. These numbers here basically just mean like prepare this qubit. It has a crazy number in the state 0. So it's like the state, the initialization bit. This is basically printed directly from the code that I'm using. And there are all the boxes, the red and purple ones with the single qubit gates, and then these the crosses with the circle. These are the entangling CNOT gates, and these are the measurement operations for all 6 qubits. So actually, there are 12 CNOTs here. They're shown these blue objects, but if you look carefully, there's actually like these 2 CNOTs they cancel. So CNOT squared, like I mentioned earlier, is the identity. So these go away, and actually these 2 unitary operations also go away, and then these 2 CNOTs also go away. So it turns out actually that you can eliminate these middle qubits or middle operations, and the actual circuit only requires 8 CNOT gates when applied to the actual environment. Okay, so here's the result. So we're computing this matrix element squared, as I mentioned, between the vacuum and some state. And so there's 2 lines here, one showing where that state is also the vacuum. So that's sort of like the no emission case. And then there's the overlap with the first excited state that's shown on the bottom here. And there are a variety of lines, but let me first just say that if you compare, for instance, the black circles and the yellow dashed line, they agree really well. And so this is really a statement that the quantum computer gives a good description of our analytic calculation. So that result is including all the digitization effects, and the blue line here is the analytic calculation where we don't have those effects. And I'm going to spend the remaining minutes that I have telling you a little bit more about what the other lines mean. So in particular, you see these green squares. The green squares say raw quantum. So that's the result we get out of the quantum computer without doing anything. And so I'll just tell you a little about error mitigation just briefly, and then also say a little about the difference between the orange dashed line, which is noiseless calculation, but with all of the digitization, and then the blue, which is the result that we can calculate analytically without digitization. But just first of all, the overall trends, this is the coupling constant. So obviously when G goes to 0, nothing happens. That's why the transition rate is at 1. And then as you increase G, right, then whether more emissions you overlap with the ground state goes down. Okay, so first let me say something about digitization. So here's a plot that shows there's no quantum measurements here. This is all in simulation, but you can get a sense for what it looks like if you have 1, 2, and 3 qubits per lattice site. And the blue is the same as the blue from the previous slide. So this is the analytic calculation, but there's no digitization. Basically the red is with 1 qubit per lattice site, which is a very bad approximation to Gaussian to have only 1 qubit, basically only have 2 values. If you have 2 qubits, you have 4 values, and 3 qubits, you have 8 values. And you can see that actually converges very quickly. So the green is basically spot on the blue, better than 1% everywhere. And this actually motivates the statement I said earlier, where I think in practice, we're going to only probably ever need a relatively small number of qubits per lattice site, but we'll want to have as many lattice sites as possible. So having an exponentially scaling Gaussian state prep, for instance, is probably not so much of a problem. Okay, so then the next thing I want to talk about is noise. So these green boxes are what we actually measure on the quantum computer out of the box. And then we have to apply some error mitigation strategies to achieve the black arrows here to go to from the green squares to the black circles. So out of the box, the results are not so good. You need error mitigation because we're not in a fault tolerant state yet. Basically, each of the qubits and the operations in Readout are all a bit noisy. Okay, so there are 2 kinds of errors that happen. One type of error called readout errors. Basically, state may be in a 1, but you read it out as a 0 or vice versa. And this can be encoded in a transition matrix. So here you can see a measured transition matrix. It's not from the same computer, it's from a different IBM computer, but it doesn't really matter. This one has 5 qubits. And so there are 32 states that are shown here, 32 true states. And the y-axis here shows all the measured states. And you can ask, if I prepare my quantum state in a certain state, what's the probability that I measured out in that state? And that would be the diagonal of this matrix. And you can see it's pretty high. In some cases, upper 70s, lower 80s percent, which is good, but it's not 100%. And so basically we need to correct for this, 2 to the n by 2 to the n transition matrix. And as a fun aside, it turns out that actually high-energy physics has proposed a lot of solutions to that problem. We call that unfolding in experimental high-energy physics. Imagine you have some differential cross-section that's binned, you want to make a measurement, you want to correct for detector effects. That is basically exactly the same as, we have a bunch of states, we measure the counts in each state to perform some expectation value, and we want to correct for, readout noise. So that's exactly the same, and you can actually apply the unfolding techniques that we developed for high-energy physics to quantum computing, which is what we've done, and is also in this paper I've written at the bottom. And the other kind of errors are gate errors. The problem with quantum computers is that you want them to be as isolated as possible. You also want to be able to touch and operate on them. So those are obviously in conflict. So every time you actually touch it, you introduce some errors. And so imagine you have this sort of simple circuit that's shown here. The idea of zero noise extrapolation is that you can replace all of the C0s, whatever your noisy gates are, with some copies of themselves, such that it doesn't change the actual circuit value, at least in the noiseless limit. So let's say you have 1 C0, you can replace 1 C0 with 2 to the n plus 1 C0. So that doesn't change the value in principle, but it just adds noise. And so you can basically increase the noise in a controlled way by measuring the expectation values at different values of n, and then systematically extrapolating to n equals well, in this case, let's say -half to get to zero noise. And there are a variety of ways to do this in efficient ways. For instance, you can think of these NIs as being themselves not all the same. And you can write down what the optimal probability distribution is for these NIs in order to use as few quantum resources as possible, which is something that we've recently done and applied to this, this case. Okay, so I now want to basically end by showing you this picture again. This is the final result of this matrix element. That's sort of the stepping stone towards something closer to what we might actually want in an effective field theory that looks something more like the standard model. We've computed the overlap with the vacuum with, say, the vacuum. That's this top line, and then also with the first excited state on the bottom here. And overall, you can see that the calculations that we've done, which is relatively small, simple, we can do it analytically, agree pretty well with the measurements on the quantum computer. All right, so that brings me to the end. I think I leave a little bit of time at the end for questions. So there's a long road ahead, but I think quantum algorithms are very promising for modeling high energy scattering. And there's clearly a lot of steps required. There's a big program ahead of us, but I think it's quite fun and there's much to learn. So obviously we have to scale up in terms of the number of lattice sites, number of dimensions. Then there are non-trivial, those are not only technical challenges, but also theoretical challenges to modify the approaches, but also then there are other technical and theoretical challenges. For instance, we want to, of course, move to gauge theory. That's what we ultimately care about. We need to establish benchmark problems, try to make sure that our algorithms are robust, and study related algorithms that might also help us tell us something. And I think what's pretty exciting is that this is a rapidly advancing area. There's growing connections between experiment theory, instrumentation, and also computing. That's it. Thank you.